Hello everyone, my name is Nawaf and I'm glad to be here to presenting my paper, Modeling and Mitigation Security Threat in Network Function Virtualization. The outline of my presentation will be introduction and then moving to the background on NFV, co-residency in NFV, and then the motivating example. Then we're moving to the modeling security threat in NFV, which including the multi-layer resource graph, modeling co-residency attacks, applying the security metrics. Then we're moving to the attack mitigation, to include the optimization-based mitigation and use cases. Then we'll show our simulation result and we will end with a conclusion. As a cornerstone of cloud, virtualization has enabled providers to deliver various cloud services to different tenants using shared resources in a cost-efficient way. The trend of virtualization has also led to many innovation in networking, inside and outside the cloud. Traditional network heavily rely on vendor-specific hardware devices with integrated softwares for these devices, such as routers, switches, firewall, and IDS. The need for separating the software from hardware and network devices has led to network function virtualization. The dependency on virtualization and the increased complexity together lead the NFV to introduce new security concept. The NFV stack involves several abstraction levels covering the physical and virtual infrastructure as well as the virtual network function. And this different layer will lead to a large attack surface such as cross-layer attacks. One of the main advantages of the NFV is to provide diverse network services to different tenants using the same hardware infrastructure, and this leading to the shared similar cross-tenant attack as those seen in the cloud. Security threat introduced by the multi-layer and multi-tenant nature of NFV need to be better understood and mitigated. As a solution in our work, we propose a multi-layer resource graph model for NFV in order to capture the coexistence of network services, VM and physical resource at different abstraction levels inside the NFV stack, and how those could potentially be exploited by attackers. We model the insider threat by malicious or compromised user of co-residence instance inside the same NFV stack. We propose a solution to mitigate security attack in NFV through VM placement and mitigation, which is a low-cost option already available in NFV stack. As a main technology pillar of network softwareization and 5G networks, NFV provides a network function through software running on standard hardware. NFV enables network service provider to deploy dynamic, agile, and scalable network services. As we can see here in the two figures, the left side, which is presenting the ETSI architecture, and they dividing into three blocks. The first one is the virtual network functions, presenting the network function that can be running. The second block is the network function virtualization infrastructure, which is including the virtual machine and the physical resource. And the last block is the NFV management and orchestration. The right side will show the multi-layer deployment models, which is dividing the NFV to 4 layers. The first layer is the service orchestration, and that layer also including the VNFs. The second layer, which presenting the resource layer, which presenting the video that running the VNF or hosting the VNF. The third layer is the virtual layer, which including the virtual machines running on top of the physical machine, and the last layer is the physical layer. And also in this model they show the relation and the connection between each layers. The co-residency in NFV as an NFV stack is a multi-layer and multi-tenant in natural, placing and migration a VM or VNF can be a challenging task for the provider due to the issue of co-residency. In an NFV stack, co-residency can happen between more layers, can happen between VNF and physical host, also between virtual machines and physical host. And these two types of co-residency between the VNF or VM with the same physical host can happen because of the placement or migration, which is known to lead to side channel or resource depletion attack due to the shared physical resources such as CPU, memory, or caches. The last type of co-residency, which is between VNF and virtual machines, and this is specific for the NFV, can happen when different tenants using the same VM to run similar network functions such as virtual firewall or virtual IDS. In this, we design a concrete example of NFV stack based on both the ETSI architecture and the multi-layer deployment model, as well as other public available information gathering from various providers and vendors. And we can see in the right side, the figure on the right side, that show the three layers, which is the VNF layer, virtual machine layer, and the physical layer. And the highlighted box that show different tenants running on the NAV stack, and we will show those different tenants on our use cases later. Both the NAV provider and each tenant may want to understand and mitigate the potential security threat. Existing threat models such as various attack tree and attack graph may be applied. There are some unique challenges and opportunity. The NAV stack is composite of different layers, and the interdependency between resources on those layers may lead to novel cross-layer attack. The fact that multi-tenants are sharing both virtual and physical resource in the same NAV stack pose another challenges. Example, co-residency attack. Virtualization NFV also provided an opportunity for mitigation security threat through unique hardening option, for example, by using the VM placement or migration. As a modeling, we're starting with the multi-layer resource graph, and our goal here is to help the NFV provider or tenants to better understand and mitigate the security threat from an external attacker, a dishonest or a compromised user or tenant, or a tenant administrator or cloud operator with limited privileges. To model the security threat in NFV stack, our key idea is to apply the resources graph concept while considering the multi-layer nature of NFV, which is the VNF layer, VM layer, and physical layer. We propose the concept of cross-layer resource graph to represent the causal relationship between different resources both inside each layer and across different layers in given NFV stack. And this our model, we dividing to the three layers, which is the first layer, the VNF layer, and show all the resource graph for this layer, and the second layer, which is the VNF layer, and show all the representative graph for this layer, and the last layer is the physical layer, which also the resource graph for physical layer, and the dashed lines that presenting how the cross layer happening between those different three layers. To model the co-residency attack, our main idea is to capture the consequence of such attack as satisfying certain conditions inside the cross-layer resource graph of the targeted tenant. And the boxes on the right side show an example of the other tenant who are using their VNF to attack the target tenant. by using the side channel attack to get access to the switch, virtual switch relating to the target tenant. Also, another example is the tenant who has a VM running on the same host, and by using the side channel attack to get access to the VM related to the target tenant. To apply the security metrics here, before we could mitigate the model security threat, we need to first quantify them, such that we could evaluate the level of threat before and after we apply a hardening option. We're using the K0 the safety security metrics, originally proposed for traditional network. This metric basically counts how many distinct unknown vulnerability must be exploited in order to compromise a given critical asset. The K0D can be applied in several ways. We could evaluate the metrics on the cross-layer resource graph of the target tenant without considering other tenants. Another scenario, we could evaluate the metric on the cross-layer resource graph, including co-residency attack from other tenants. Also, we could evaluate the metric before and after applying placement or mitigation-based hardening options. As an example here, we have a tenant, a malicious tenant, who has access to the firewall running on the VM by exploiting attacking the physical host. This they can reach and applying another exploit to get access to the VM that relating to the target tenant to reach the critical asset, and we can see here they only need to have two exploits to get reaching to the target by using the multi-layer attack. And this attacker, which is a malicious user who has access to the VM running on the same host that run VM relating to the target tenant, and by exploiting the first exploit, which is the second exploit, which is in the database. The first one was the side channel attack, the second one on the database, and the third exploit that he needs to exploit it, which is to the physical, to get access to all VM running on that physical, and the K in here is equal to 3. To optimize, we use the genetic algorithm to optimize the VNF placement and mitigation for maximizing K. The cross-layer resource graph is taken as input to optimization algorithm with K as the fitness function. We try to find the best VM placement within a reasonable number of generations. The constraint we have considered include specific VM can be assigned to each host, so we can use this constraint to make some hosts that can be running only specific VM, like database, or maybe running VNF that running the firewall or running IDS. Also, we enforcing a given placement policy using in the Cloud SIEM. Also, you can satisfying by what the maximum number of migration VMs that can be used to find the ways of the or we can explain more better in this constraint we can maximize putting maximum number of the VM that can be moving from host to another host. In this use case, the first one, we will show how is the attacker can moving in one layer. So by to reaching the target, which is the root one, and the attacker here, which is the malicious, who has access to the VM running on the same physical host that run another VM relating to the target thing. So the attacker can move in here by exploiting 3 different exploit to reach the target. Another scenario, by using the cross layer, so the attacker here who has VNF surface run on the same VM related to the target tent, and by using the cross layer, the attacker can reach the same goal with the k equal to 2. In this case, we show the optimal placement result for our motivating example. As we saw there, we have 3 different colors: the blue relating to the Alice, green was to the Bob, and the red for Melor. And Melor is a malicious here, and we can see on the left side table, the top table. And in this, if the mitigation happening or by the tent, by switching the VM that he's running, and we can see before applying the mitigation k was equal to 2. After we applying the mitigation by the tent, k was increasing to 4. But when we applying the mitigation by the provider, k was increasing by 5 because the provider can mitigate migrating VM for different tent to increase the security here. In the simulation results, we study how cross-layer attack may affect the security of the NFV stack. We compare the K0D metric on the original resource graph without any cross-layer attack and cross-layer resource graphs. And we can find that the value of K decreases in all cases almost linearly. This is expected because as the size of the network increases, there is a higher chance for the length of the shortest path to decrease, which means attacker may require less attack steps. Also, we find that the value of K drops on the original resource graph without considering cross-layer attack. After considering the presence of malicious tent, the co-residency attack, which is expected. Finally, the value of K dropped by approximately 55% between the original resource graph without considering the malicious tent and the cross-layer resource graph, which show the additional threat of the cross-layer attacks. We show in the second simulation how different placement policy can be affecting the value of K. We employ the cross-layer resource graph to measure the value of K for 3 types of attacker: external, malicious tent, and lower layer provider who has access to all hosts. And the 3 different placement policy used in CloudSim: the most policy, the least policy, and the random policy. And we can find that the trend of the external attacker and malicious intent decrease faster than the lower layer provider. This is expected because the lower layer provider already has access to all the hosts, which enable him to either use his privilege to attack higher layer, which mean much lower K value and hence less room for the further decreases as the network size increase. The most placement policy has the highest value of K, both external attacker and malicious intent, and the lower K for lower layer. This is because under the most policy, the target tent VM tend to stay closer to each other, which rendered them less vulnerable to external attacker or malicious intent, but more to the lower layer provider management, the host of such VMs. For this simulation, we study how the number of malicious intent can increase the insider threat under different placement policy, and now the mitigation solution may improve the value of K in each cases. And we can see that the mitigation solution successfully reduce the insider threat by increasing the average of K value in all cases. Also, the result of random placement policy after applying solution is slightly better than the result of the most placement policy before applying the solution, which means that the mitigation solution may improve the placement algorithm with regard to the co-residency attacks. To conclude, we have model cross-layer and co-residency attack and the NFV stack. We have also formulated the optimal VM and VNF placement problem to mitigate the security threat through standard optimization algorithm. Also, we conduct the simulation whose results show that our solution could significantly reduce the level of security threat and NFV. For the future work, we will make our solution incrementally and more efficient in order to handle more dynamic in terms of VM placement and immigration. We will consider weight different exploit and asset value to optimally choose among those different options for given NFV application. We will study the integration of our solution with existing deployment policy based on NFV testbed. Thank you very much.